Hello friends, welcome to Mu Lessons. Today we will discuss about the PN junction diode, how the PN junction diode are used in our daily lives. So this is a simple diagram, or this is a pictorial view how to use this PN junction diodes. PN junction diode is a combination of P-type and N-type doped with, or you can say sandwiched with each other. So this is the well-known diagram for PN junction diode. This stick part corresponds to the negative part and the delta part is the positive part. So we'll study it as we go through this. Now how this PN junction is formed? We have two types, that is the P-type and N-type materials. In case of P-type materials, you can see this semiconductor materials doped with acceptors because they are positive. Now this kind of materials have high hole concentrations. Here are a number of holes you can find, and the concentration of the free electrons in P-type material is very low. The number of holes is always more than the number of electrons in case of P-type semiconductors or P-type materials, and it is just the opposite in case of N-type materials. In this case, the semiconductor materials are doped with the donors. They have high concentration of electrons, and the concentration of holes in N-type material is very low. So now coming to the doping part. This P-type materials contain a negatively charged acceptors and positively charged holes, so the total charge in this case is 0, remaining the equality of charge and making the substance neutral. Similar to the N-type material also, it makes the substance neutral because it contains the positively charged, which are the donors, and a negative charge free electrons, so the total charge is also 0. Now what would happen if this N-type and P-type materials are in close contact with each other? Now this is the P-type and this is the N-type. We have made them close contact with each other, or you can say by doping. The free particles or electrons start diffusing from the N-type materials into P-type materials. Please do not misunderstand that this P-type and N-type junction will be formed if you just stick them together. Though in that case the rough surfaces are so large for the electrons to jump from one part to another. So combining these two means doping them with each other, melting them and suddenly cooling them at this part. So being the free particles, electrons start diffusing from the N-type material into P-type material, and the holes start diffusing from the P-type to N-type. Now however, every electron transfers a negative charge of -q and P side, and also leaves a uncompressed of +q on the donor side. Every hole creates one positive charge q on the N side, and similar to that it has -q on the P side. So this results into this depletion layer. There is a potential difference between these positive signs and this negative sign, and this is known as the depletion layer. The electrons and holes stay close to the PN junction. This is a PN junction because the negative and positive charges attract each other, and this negative charges stops electron from further diffusion, and these positive charges don't allow the holes for further diffusion. So the equilibrium is made in this case. The diffusion from the dipole charges layer at the PN junction interface, you can see from this picture. Now there is a built-in voltage between these types of charges, that is the negative and positive charge across the junction. This is known as the built-in voltage, and this prevents the penetration of electrons and holes from the either side of P side and N side. Now what will happen if a voltage is applied to this PN junction diode? Now as the given polarity, it attracts the holes from the left and electrons from the right, and according to the current continuity law, the current can flow in all the charged particles, forming a closed loop, and that will complete the circuit. However, there are few holes in the n-type materials and there are few electrons in the p-type materials. There are very few carriers, they are known as the minority charge carriers, and there are very few carriers available to support this current through the junction plane. So the voltage polarity shown, the current is nearly zero in this case. Now what will happen if the voltage polarity is reversed? That is, the p side is given the positive terminal and the negative, and n side is given a negative terminal. In this case, it will attract the electrons to the left and the holes to the right. As we know, there is a plenty of electrons in the n-type and plenty of holes in the p-type, so there will be lot of movement of electrons and holes. So there is a lot of carriers available to cross the junction. So when the voltage is applied in lower than the built-in voltage, the current is still zero. You must remember, this is the depletion layer and it has a depletion voltage, or you can say the built-in voltage. When the potential is greater than this built-in voltage, then only the flow of carriers is possible. Until then, the current is zero. And when the voltage exceeds the built-in voltage, the current can flow through the PN junction easily. Now when the diode is active, or you can say the carriers are moving from one part to another, we have a current equation on the basis of experiments. This current across the diode, this I is known as the diode current, is given as Is into exponential of QV by KT minus 1. K is the Boltzmann constant, T is the temperature, and remember KT by Q is given as 0.26 volt, 0.026 volt, sorry. And the value of Is, that is the saturation current or the diode current, which is very small, is nearly equals to 10 to the power minus 17 to 10 to the minus 13 ampere. When the voltage V is applied, that is the forward polarity, the exponential terms increases rapidly with the voltage V and the current is very high in this case. Now this is the IV characteristics, current voltage characteristics of the diode. The first quadrant shows the forward biasing of the diode, that is the active region, and the third quadrant shows the reverse bias condition. Now we always have to connect the PN junction in this manner, that is, this is known as the forward biasing condition, positive terminal to the p-type, negative terminal to the n-type, and the diode equation or the diode current is given as I equals to Is exponential of QB by KT minus 1. Now at room temperature we can also get the simplified version. We know the values of KT, we will write I equals to exponential of V by 0.026 minus 1. So it is similar to the previous one. Now some experimental studies have shown the graph of forward bias and reverse bias characteristics. The first quadrant is the forward bias characteristics. Whenever the voltage increases the built-in voltage, that is 0.7 for silicon and 0.4 for germanium, after that a small increase in voltage will cause a large increase in the current, and this is the forward characteristics of the diode, silicon diode, because the built-in voltage in this case is 0.7. And similarly in case of reverse bias condition, we will have a reverse breakdown voltage, that is that point of voltage at which the current increases rapidly for a very small increase in the voltage, and that occurs always in the reverse bias condition. Now the circuit notation for PN junction diode on the first page you have seen. Again I want to revise this. When the diode is connected in this format, it means the picture view is PN connected as shown in the figure. P type should be connected to the positive type and N type to the negative type. When the plus is applied to the P type, the current is high and this is the forward condition, and when the plus is applied to the N type, that is the current is nearly zero, that is a reverse bias condition. So when the diode is connected in this manner, we will get the forward characteristics, and when the diode is just reverse, we will get the negative characteristics or the reverse bias characteristics. Now there are several uses of rectifiers, we will read in details in the next video. about half wave rectifier, full wave rectifier, clipper, clamper, etc. So these are just pictures of how this diode can be used as half wave rectifier. In case of half wave rectifier, we only use a single diode, and for this value of input we get this output because the negative part is clipped up in half wave rectifier. Rectifier generally means conversion of AC voltage to DC, or generally from AC source voltage source to DC. In case of AC we have a changing magnitude, changing polarity, but in case of DC we will have the same magnitude and there will be no change in the polarity. Similarly, to get more efficiency we use the full wedge bridge rectifier. This is the diagram of this full wedge bridge rectifier, and in this case there is no change in polarity and we get the same negative potential also on the upper side, on the same side of the positive part. So this is the difference between half wave rectifier and full wave rectifier. We have explained it before on brief and in more detail in the next video. Now these diodes can also be used as light emitters, photodiodes. In case of light emitter diodes, or you can say the LEDs, what happens when we supply current, this current is taken by this p-n junction diode and it emits light, and this always works on the forward bias condition. The electron drift into the p material and finds plenty of holes. They combine with the filling of the empty positions, and these holes drift into the n particles, n materials, and fill the electrons there. So there is a recombination of the empty regions. And the ejection of photons is the particles of light we get. It acts as a LED, that is a light emitting diodes. Now just the opposite of LED, this is the photodetectors. In case of light emitting diodes, you have to connect this source as positive, and so that the diode will act in the forward bias condition. But in case of photodetectors, it is just reverse. The source is reversed and the p-n junction can detect the light in the reverse bias condition only. So what happens in these photodetectors, whenever light falls on this diode, the photon's energy releases the free holes and electrons, and that helps in conduction. The applied voltage separates the photocarriers, attracting electrons towards the plus and the holes toward the minus sign. So as long as the light is on, the current flows through the p-n junction diode and it conducts. And as soon as the light is removed, there is no more flow of electrons or current and the circuit is closed. Now this is the diagram, or you can say the graph of p-n junction diode. We have read this before also. Now just applying the Ohm's law, you can get E is equals to VR plus VD from this circuit diagram. So whatever may be the connection, your base should be clear how to apply this Ohm's law, Kirchhoff's law, and that will help you later in solving problems and studying the full wave, half wave rectifiers, clipper, clampers, etc. Now here is one interesting part for you that is how to solve a circuit with a p-n diode. Now we can solve this by varying, there are two methods, by varying VD. Now assume we have a diode voltage of VD, we can calculate the diode current also. Then when we have the current, we can find VD and VD plus VR. The sum must be equals to this EMF net E. So E is equals to VR plus VD. From the circuit diagram you can see. So VR is given as I into R plus VD, and this I, that is a diode current, is given as IS into exponential of QVD by KT minus 1, or you can say exponential of V by 0.026 minus 1. Now this is the second method, that is a load line analysis. Load line analysis means the intersection between the load line and the characteristics or forward characteristics of the diode. In this case we have to consider VD as a variable and we can calculate the diode current ID. So by using KVL law, we have the diode equation as ID equals to IS exponential of q Vd by kt minus 1. We will use it in this formula, and by using KVL we will get the current across this VR by RB. So there are two approaches for these two currents, that is ID and IR, and that can be plotted. In case of series circuit, this ID is equals to IR, that is the diode current is same as the current flowing through this circuit. So I will show you the simulation also working with these problems in MATLAB in this part, how to solve this question in MATLAB, and you will get the load line analysis also. Now in this case, this is the MATLAB window. I will show you how to get the results or the load line diagram in using MATLAB also. As an engineering student, you must be knowing about this MATLABs. I have provided the video on MATLAB basics and its simulation previously. So I have arranged a question and a solution for you. So this is the program which I have written. This is quite simple. You need to write clear all, close all. The EMF value E is given as E equals to 2. RB, that is the resistance value, is given equals to 20. And IS, that is the current, IS equals to exponential 2E minus 12. This is the format of writing exponential in MATLAB. And KTQ is given as 0.026 KT by Q. EV max is E, and we have to plot the VD, and that starts from 0 to V max, and the unit difference is 0.001. that is the difference. So we have the diode equation as ID equals to IS into exponential VD by KTQ minus 1, and this is the device and circuit parameters which you have given. And now for the graph, for the load line, we have IR equals to E minus VD by RB from the circuit diagram. You can see, you can refer to the circuit diagram, and similarly all the values have been entered. At last we have plotted all the diagrams, all the graphs, and X level is given as current, X level is given as voltage, and Y level is given as current, and we have also assigned a axis. Now this keyword grid on is used to apply these grids on the circuit diagram. So now we will run this, and here it comes. You can see this diagram. This is the load line analysis. This is the forward biasing current, blue line current, and this is the green line which shows the load line. The intersection of this forward bias characteristics with this load line gives the Q point. This point is called the Q point, or you can say it is the operating point. And this operating point is used mainly. This is the operating point. So by solving all these type of diagrams, you will become quite aware of how to use them, and this is the most simplest way of simulating them in MATLAB. So these are the simple things you can read in basic electronics. You can simulate them in MATLAB, so both of them will be clear simultaneously for your studies. Hope you like this video. Thank you.